Welcome class to our guided notes section on Skill 8 from Unit 5. This will be on just part 1 of applications of exponential models. We'll be focusing mostly on appreciation, depreciation, and compounding interest in this example set. So I wanted to start us off with the basic formulas we'll be using for the examples. You can see that in all these formulas there are quite a number of letters representing different values. So I wanted to point out which ones are the actual variables in each question. So maybe we'll start with the standard appreciation formula. Okay, so we have A, which is the final amount, or the final value of something. P, which is our initial amount or initial value. R, which is the rate. So this is a percentage, but written as a decimal, and it's the annual interest, or maybe I should call that annual appreciation rate, since in this formula we're thinking about something appreciating. And then T is time. Okay, so what happens is in this formula, A is like the Y value, or like the Y variable, the way we're used to thinking about Y. And T is like the X variable, the way we're used to thinking about X. Of course, we're calling them A and T in this formula, and in different examples we might call them different things. But this final amount is basically our dependent variable, like the Y variable typically is in our other functions that we've learned. And T is our independent variable, which is like the X value in the other types of functions we have learned. Okay, so only A and T are actually going to be varying. Okay, these are the only actual variables, whereas P and R remain constant. Okay, these are constant values within an example. Once we have determined the initial value of that thing, and once we have determined the interest rate or appreciation rate, those values stay constant. They don't change within an example. They stay constant, and these are really just representing numerical values. Whereas T is a variable where we can plug in different times. We can kind of, just plug in different time values just to see, well, what will the amount be in 2 years? What will the amount be in 3 years? We can kind of see how the time affects the amount and how long of a time we need to get to a certain amount and that kind of thing. So only the amount and the time are actual variables. And that goes for these other formulas as well. So the A and the T in each of these formulas are the actual variables. Okay, A is the Y, T is the X in all of these instances. And every other letter that you see in those formulas is representing some type of constant. In fact, oftentimes it's the same constant. Which is why I use the same letters and colors throughout, so you can kind of really begin to visualize where all of these particular constants go, right? We've always got the right side starting off with the letter P, right? P, 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 P. So we always begin with the initial amount. So P stands for principal, okay? Principal, which is another way of saying like what you are beginning with, the starting amount, the initial amount. The equations always begin with that. What was the initial amount? What was the initial amount? What was the initial amount? We always begin with P for principal or initial amount. And then it's always followed by, or most of the time followed by, a 1 plus. In this instance, it was followed by a 1 minus, and then in this instance, it was followed by E. And we'll talk about that one in a second. And then immediately after that 1 plus or 1 minus, we see R. R, which is referring to that annual interest rate. In these formulas, we write it as a decimal, okay? Here it's still referring to that annual interest rate as a decimal, but you'll see it's in the exponent for this last formula. And so the interest rate, again, is constant for each of these. Once you figure out what it is for a given situation, it's always going to be that same rate for that given situation. So it's a constant value, and it always or generally follows a 1 plus or a 1 minus. And then the T is always in the exponent. The time is always in the exponent, which is why these are called exponential models, because the variable that's acting like X is in the exponent spot. That's what makes these exponential models. Let me talk about this depreciation formula really quick. So In the appreciation formula, let me erase some of this stuff. I just want to kind of help you understand also like why it's set up the way it is, okay? So in the appreciation formula, you see that we begin with an initial amount P, and then we multiply that to this quantity 1 plus R. Let's just ignore the exponent of T for a second and just think about what this is saying. An initial amount times a quantity of 1 plus R, where R is representing a rate, a percentage rate. It's written as a decimal, but it's representing a percent. Well, this number 1 right here is representing 100% when you write it as a decimal, because 100% as a decimal is 1.00. So that's what this 1 is. This is 100%. And when you multiply that by P, that basically just means 100% of P. So the 1 is really just representing whatever that initial amount was because it's being multiplied to P. So then when you add R, which is some percentage rate as a decimal, when you add that to 1, you're adding it to 100%. So you're kind of saying 100% plus this percent, which is why it's appreciating. It's increasing in value because you're taking a percentage and adding it back to 100%. So then the result will be over 100%, more than the original amount. And then you're doing that, once each year for an indefinite number of years. So you have to, for each year, you take that rate and you add it back to 100% of P. And then you do it again the next year, and then the next year, and then the next year. And for every year you do it, you're multiplying this back to itself, which is why we raise it to the power of T, because you're multiplying the same quantity over and over and over again. And the power is telling you how many times you multiply that quantity, and then that's getting multiplied to that original amount. And then this is, when you multiply that all together, that tells you how much you would end up with, which is obviously going to be more than 100% of P. So A will be more than P. The final amount will be worth more than, or the final value will be more than the initial value, because the value has appreciated because we have added a certain percent to 100%, causing the result to be greater than 100%. And we've done that for however many years, and so the value just goes up and up and up and up and up. Okay, that's appreciation. Depreciation, by the way, is pretty much the exact same thing, except that instead of adding the rate to 100% of P, you subtract the rate from 100% of P, which means that the result A will be less than the initial amount P, because it will be smaller than 100% of P. We would have taken something away from that 100%, making it smaller than 100%, and we would have done that for a certain number of years. And after so much time, we can see, okay, this value has gone down to whatever it's gone down to, but it's less than the initial amount. So this is the only one, the only formula where your final amount will actually be less than your initial amount, because it's the only one where you're actually taking something away from 100%. Okay, now, when we start looking at things more related to interest, and looking at different savings accounts and this and that have interest, we don't always only compound the interest once per year, as in the standard appreciation model. Sometimes we compound the interest in intervals, more than one time per year. And so that's why we had to introduce this new constant, n. And n is referring to the number of times per year. So you have this annual interest rate, and that interest rate is the rate just for within that 1 year. But sometimes within that 1 year, you will add that to the principal more than one time. You'll add it n number of times to the original amount. But what they do in those situations is they don't take the whole rate and add it to 1. They take a fraction of the rate. So they decide how many times they're going to be compounding that interest. They divide the rate up that many times, so they get it in n equal parts. And then they add that fraction back to 100%, but they do it n times within the same year. So that's why the number of times that they're adding this back to, or the number of times they're multiplying this to the principal, is not just t, but n times t, because it's n times within a given year times however many years. is how many times we've actually added this rate to the principal to get our final amount. And so that's why we have to introduce this n, is if you compound more than one time per year. Notice that these formulas would be the same, though, if n was equal to 1. If n was equal to 1, it would just be 1 plus r, just like it is here. If n was equal to 1, this would be 1 times t, just like it is here. So these two formulas are the same when n equals 1. Okay? Now, let's go down to compounding continuously, and then you'll notice, oh, there's that number e. We recently learned about e. As a reminder, it's approximately 2.72 if I round. Of course, we know the decimals keep going, but if I round it, it's about 2.72. And if you remember, this number e was the result of letting n approach infinity in this expression. We got this value e when we took 1 plus 1 over n to the power of n and let n approach infinity. Now, what is n in this context? So look at this here. Compare this to my appreciation or interest compounded in intervals. Ignore the r for a moment. Imagine that there was just a 1 there. And ignore the t for a moment and imagine that was just a 1. You'd see we have 1 plus 1 over n to the power of n. The same exact expression that we looked at on our notes a couple weeks ago. If I let that n in that expression approach infinity, then that expression turns into this constant e. It becomes this constant e, which we understand is about 2.72. So that's what's happening when you let something compound continuously, because n is referring to a number of times. It's the number of times per year that the interest compounds. So if you let it compound continuously, you can think of that as infinitely many times. That's like saying, hey, let's take this formula and let n go to infinity. That's what that's saying when you say compound infinity. That means n is approaching an infinite number of times. And then this part of that expression is approaching e. But we still have this rate and we still have this time, this exponent of t, and r is being raised, or this expression is being raised to the power of t. So r is part of that, being raised to the power of t. And a power to a power, they multiply together. And so that's how we end up with e to the power of r times t in our compounding continuously formula. So really, these two formulas are also the same when n is equal to infinity. When n is equal to infinity, this turns into e to the power of rt. When n is 1, this turns into 1 plus r to the t. So these three formulas are really all stemming from this one here. This is kind of like the original one. And when n is 1, you get the standard appreciation formula. When n is infinity, you get this compounding continuously formula, which sometimes people refer to as PERT, because it's p times e to the rt, principal initial value times base e to the powers of r times t. And that's basically this same formula once you've let n go to infinity. So this compounding in intervals formula is really everything in between 1 and infinity. If you have it compound 2 times or 3 times or 10 times or something, some number of times that's more than 1, but not quite continuously, not quite infinity. So that is kind of the background of all of these formulas. Now we're going to go ahead and look at some examples and apply these formulas. So let's take a look at number 1, talking about appreciation. And let's say you wanted to figure out what the yearly appreciation rate was on your home. Let's say you purchased a home for $200,000, and that was 5 years ago, 5 years in the past. And then today it is now worth $230,000. Let's say this is the scenario, and you're trying to figure out, what is that yearly appreciation rate? So that you can maybe see a few more years down the road, what it might be worth. Okay, so we're going to use our standard appreciation model to determine that. The standard appreciation model is the one where you just add R to the 100% one time for a certain number of years. One time per year for a certain number of years. So we have to figure out what all the pieces are, okay? So it looks like in this scenario, our initial amount was $200,000 because that was what it was worth 5 years ago, right? This is initial. Okay. And then our final amount, we can think of that as what it is currently worth, right? This is the current value, okay? And then T is actually given. This is 5 years have passed. So actually T in this particular case, we can plug in a value for. The R is the thing that we actually don't know. The yearly appreciation rate. What is that? We're trying to find the yearly appreciation rate. So what I'm going to do is plug in all these numbers into this formula, and then I'm going to solve for R. So I'm going to plug in 230,000 for A, because that was the initial current, that was the final, which is the current amount. I'm going to plug in 200,000 for P, since that was the initial amount. I'm going to multiply 200,000 by 1 plus R. Notice I'm leaving R as R because that's the one thing I didn't know. And I'm going to raise that to the power of 5. So this is my A equals P times 1 plus R to the T, but with values plugged in for A, P, and T. And then I'm going to solve for R. Solve for R. So R is inside this amount being raised to the 5th power. So what I want to try to do is isolate that power. I'm going to isolate that power. And the way I'm going to do that is dividing both sides by 200,000. So that'll get rid of that. And then over here I have 1.15. And then on this side I just now have the 1 plus R to the 5th power. And I'm trying to solve for R, right? So I need to undo an exponent of 5. I need to cancel an exponent of 5. So what I'm going to do is a 5th root, because a root can cancel a power, because roots and powers are inverses. So I need to find the 5th root of 1.15. I need to figure out what that is in my calculator. And then that will be equal to 1 plus R. Okay, so let's do the 5th root of 1.15. Now, you might be wondering how we can do that on a calculator. Well, it might be easier actually to think of it this way. 1.15 to the power of 1/5. That's using a skill from Unit 4 that says that a root can be written as a rational exponent where the denominator is the root. So a 5th root is really a power of 1/5. And then we can find that on our calculator. Here's a quick peek on Desmos. You can see it's about 1.0283. And that is currently equal to 1 plus R. So to get R, to solve for R, I would just need to subtract 1 from this number. And so R would equal 0.0283. But what is R? R is an annual interest rate expressed as a decimal, right? So this is the decimal value for the percent. So I could then say that that annual interest rate or appreciation rate as a percent, this would be 2.83%. So it's appreciating at about 2.83% per year approximately, right? Because we just kind of looked at growth over 5 years. We kind of looked at it as more of like an average rate of change over 5 years. It looks like it's appreciating at about this percent on average per year, 2.83%. So what I wanted you to do now, just to kind of see and realize that this, I'm not just making this up, right? This is kind of how we do things. I thought maybe I'd have you visit this website. So if you could click on this link or copy this link and put it into your browser, let's just take a look at this website and see how they walked through this problem. Okay, so just so you know, they kind of set up a similar example for this person to kind of walk through. This is a website just helping somebody learn how to calculate appreciation, which is what we're doing right now. So they give this setup here that, let's say you purchased your home for $200,000 5 years ago. Now it's equal to $230,000. How would you then figure out your yearly appreciation rate? So this is what they tell them to do first. They tell them to divide 230,000 by 200,000. That's right. Instead of setting up an equation, they just say, okay, well, first divide current amount by original amount. Well, let's compare that to how we began. So we began by putting this equation together, but look, the way this equation is set up for us trying to solve for R, the first thing we have to do, right, the first thing we ended up having to do was divide 230,000 by 200,000 to figure out the increase, right, the percent increase that was experienced here. But that's just a natural course of action when you set this up into a formula. Okay, and then if you go back here, they say, okay, you got 1.15, right, just like we did. Sorry, ignore all these ads, I apologize. Then step 2 says, raise the result from step 1, right? Step 1 is where we ended up with 1.15. So raise the result from there to the 1 over t power, where t is the time in years that the appreciation took place. So in our example, that was 5 years. So they took 1.15 and raised it to the 1/5 power to get 1.0283 like we got. But notice how they just kind of say, okay, take your answer, raise it to the power of 1 over t. Okay, so that's because in the formula, your rate is always being added to 1, right? It's always 1 plus r to the power of t. And if you're going to get rid of that power of t, you're going to always have to take a tth root on the other side. You're going to always have to do the root of whatever this power is to get rid of the power so we can solve for r. So that's why they're telling this person to raise it to the power of 1 over t, because when you take a 5th root, that's really the same thing as a 1 over 5 power. Or if you take a t root, it's a 1 over t power. So that is what we ended up doing because we were trying to cancel the power of 5, right? So we raised the other side to the reciprocal power, 1 over 5. And we got the 1.0283 that they got as well. But if you look in the equation, that's equal to 1 plus r. So then what do you think they tell this person to do next? They tell them to subtract 1 from the result. Because in the formula, the reason you subtract 1 is because in the formula, it's always 1 plus r. So once you get that alone by doing the 5th root or raising it to the 1 over 5 power, that is equal to 1 plus r. And if you're trying to solve for r, you subtract 1 to get the 0.283. And then the last thing they tell them to do is just to multiply by 100, because to just convert that decimal to a percent, you multiply by 100. Well, we just kind of moved the decimal to the right 2 places, which is what happens when you multiply by 100. But I just thought it was interesting to see, instead of giving them a formula, they just kind of give them the steps for solving for r in that formula, which only works, like these steps only work if that's what you're trying to do with that formula. The power of having the formula is that you can plug in different values in any part and solve for any part, which might involve different steps. But you can see we did the correct steps for solving for r in this instance, at least as was outlined by this website. So I just thought that was interesting for you to take a look how other places in the world might explain to someone how to do this. I think having these formulas is really handy. It's a very powerful tool because it essentially sets you up to do all of the correct steps already to solve for whatever variable you want to solve for. All right, so moving on to example 2, I thought we would play around with the different types of compounded interest so you can kind of explore the compounding in intervals as opposed to compounding continuously. So let's just kind of set up the basics. So in this example, we're saying that you invest $2,500. So that's going to be our principal. That's going to be our initial amount in this particular example, and it will always be that, right? This is a constant, $2,500. Okay. The question wants to know, what is the balance? Well, balance is another word for final amount or current amount. Final amount, which is the balance, which is what we're trying to decide. So we want to know what is A. And we're going to go ahead and find the amount of interest too, but that'll be a separate part later. So what is the final amount as well as the interest earned after 4 years? Okay, so then T is going to be constant in this case as well. So we're looking at, so A is the unknown amount, right? We're trying to find A when the initial invested amount is $2,500, the time is 4 years, and then in part A, it's saying that it's compounded monthly. Okay, so what does that mean? That means 12 times per year because there are 12 months within a year. It'll compound once each month, so that's a total of 12 times per year. That's going to be our value of N. Okay, so we're going to use this formula. P times 1 plus R over N to the power of N times T. Because I have to, because N is not 1 and it's not E. Compounding monthly is not the same as compounding continuously. This just happens a fixed number of times, 12 times exactly per year. So I have to use this formula here, and I'm trying to find A. So I leave A as a variable, but I'm going to plug in 2,500 for P. I'm going to plug in 0.015 because remember we turned the percent into a decimal, so we have to move the decimal 2 spots to the left to do that. And it's going to divide that rate by 12. So I'm kind of taking a 12th of that rate, adding it to 100%, and I'm doing that 12 times 4 years. So 12 times 4 total times is how many times I add this fraction of a rate back to 100%. Okay, so then that is equal to 2,500 times, I'm going to figure out what this would be, the 1 plus 0.015 over 12. And it's about 1.00125. 1.00125 to the power of 12 times 4, which is 48. And then that turns out to be $2,654.49. So that's the amount or the balance in the account after the 4 years. So that answers the amount question, which is why it's in dollars and cents, which is why I rounded it to 2 decimal places. But it also wanted us to find the interest earned. So what is that? The interest earned, let's do this over here. That's just the difference from what was originally invested, right? $2,500 was originally invested. Now I have $2,654.49. Just take the difference between those, and you can see, okay, you earned an interest of $154.49. So total amount in the account, right, includes what you originally deposited plus the interest you earned. That's this value here, $2,654.49. The difference between the two just tells you how much interest you actually accrued over that 4-year period of time. The other part of this question wants us to figure out what would the final amount be in the interest earned if I had an interest rate of 0.7% and it's compounding continuously. When you see this word continuously, that's when we want to kind of think about, okay, the number of times per year has gone to infinity. This is the Pert formula. This is where I'm dealing with E now, a base of E. So my principal is still 2,500. My rate is now 0.7, but actually as a decimal it'd be, sorry, this is percent. As a decimal it'd be 0.007. You move the decimal 2 spots to the left. And then the time is still 4 years. So the principal and the time have stayed the same, but for this case, the rate is different. So the amount would be 2,500 times a base of E raised to the power of 0.007 times 4. And you can just plug all that straight in your calculator. Let's do it on Desmos and see what we get. And it looks like I have about $2,570.99. $2,570.99. Okay, so then the interest earned here is just the difference of that and 2,500. So the interest earned here we can see is $70.99 in the same amount of time, right? In 4 years. Okay, let's move on to example 3. What I want you to get practice on here is learning how to write your own model and understanding how to set it up and how to use it and all of that. So let's look at this scenario here. So we're investing $500. that's going to be our principal. That's going to be a constant amount for this whole example A, B, and C. It's giving us our interest rate, but we're going to convert that to a decimal, so 0.05. And that's going to be our R, and it's compounding twice a year. So N is going to be 2, which is the number of times per year the interest compounds. And so what I'm going to use is this formula here, where I have the R over N to the NT, because I have twice a year, right? It's more than once a year, but it's not quite continuously, so I need this one with the N in it. But notice it wants us to create an equation A of T that would represent the amount after T years. So this wants us to set up an equation where I have a dependent variable and an independent variable. So the dependent variable, we're going to call that A of T, and that is going to represent our A. That's going to go in place of A. And when I call it A of T, that doesn't mean A times T. It just means the amount as a function of time. It's a function of T. T is our independent variable, right? Independent variable would be T. So it's not asking for a numerical answer here. It's asking for an equation. But we're going to use this formula to help us write it. So our equation for this example would be, okay, my amount as a function of T in this particular scenario is going to be my principal of 500 times 1 plus 0.05 over 2 to the power of 2t. And let me simplify this a little bit. So I get A of T, final amount as a function of time, is equal to my initial investment times the rate 1.025. So it's basically 102.5% to the power of 2t. So that's our function, right? This is our model, you could say, for example 3. And I can use it to answer parts B and C. So then, how much will the investment be worth after 10 years? This wants me to find the amount at time 10. What is the amount after 10 years have passed? Well, all I have to do with that is take my model and plug in 10 for t, right? The amount at t years is equal to all this to the power of 2t, so the amount at 10 years is equal to all that to the power of 2 times 10. And so it ends up being about approximately $819.31. So after all that time, we've accrued quite a bit of interest. Of course, that's a nice hefty percent, right? 5%. Accrued quite a nice bit of interest over that 10-year period. And after 10 years, this is the final amount in the account. When will the investment be worth 1,000? Well, now they're saying A of T is 1,000. Right? It's worth this, and we want to know what value of T makes that happen. When, right? That's a time. Well, I take my equation, I plug in 1,000 for A of T. Everything else stays the same. I keep the T there. Okay, so now I'm solving for T. So I'm going to need a log in this example because I have to solve for an exponent. But before I do that, I want to isolate the exponential part. So first I'm going to divide both sides by 500 because I'm trying to isolate this part. And I get 2 is equal to 1.025 to the power of 2t. So I'm at the point now where I have the exponential part has been isolated. So this is where I can rewrite into log form. So we just recently learned how to do this as well. We can rewrite into log form. And so I get the log of base 1.025 of 2 is equal to the exponent of 2t. So log base 1.025 of 2 is equal to 2t. Let me move this over here. I'm going to use the change of base formula to just quickly and easily evaluate this. So this is the log of 2 divided by the log of 1.025 is equal to 2t. So I'm going to get a decimal value for this, and then I'm going to divide it by 2. So I'm going to divide both sides by 2. So I'm going to get a decimal value for that on my calculator and then divide it by 2 to get t. And then this will result in a t of is equal to about 28.07 approximately, 28.07. And then I'm going to divide that by 2, and it's about 14.04. So approximately 14 years. When will the investment be worth $1,000? It's going to take about 14 years to get to that point, to get to the $1,000, to double in value, basically. So here in example 4, we have a scenario where we have Julia who has invested $1,000. That would be her principal or her initial amount. She has deposited that into a certificate of deposit 3 years ago. Certificate of deposit is called a CD. So now, today, the CD is worth $1,276. So this would be her final amount, like the A value. This is the initial amount, which is the P value. And the time for this case is 3. So this is just telling us how much time passed to go from 1,000 to 1,276. And then here in part A, it again tells us a little bit more information. It tells us that the interest was compounded monthly. So since there are 12 months per year, that means in this scenario, our N in the formula with N in it will be 12, because if it's compounding once a month, then that would make it 12 times per year. And so the question we're actually being asked here, so the what, is the interest rate. The thing we're being asked to find is the R value. So we're going to use this formula, the one where it's compounding N times per year, and we'll plug in all the different pieces, and basically what we're going to end up having to solve for is R. So that's the thing that will be left as a variable that we're actually going to try to solve for. So I'm going to go ahead and plug everything in. So I have 1,276 for A. I've got 1,000 in place for P. I'm going to leave R as R. I plug in 12 for N and 3 for T. So all of this is being raised to the power of 36. So I think what I'll do first is I'll go ahead and divide both sides by 1,000. So that becomes 1.276 is equal to 1 plus R over 12 to the power of 36. Okay, so the variable that I'm trying to solve for, which is R, is inside of this parentheses, which is being raised to a power of 36. So what I'm going to have to do to solve for R is cancel out that power of 36. Well, we had done this in our first example. We had a power of 5 in our first example, and so we had to use a fifth root to get rid of that power of 5. And it'll be the same situation here, except that now I have a power of 36. So I'll have to use a 36th root to cancel that out. So that's what I will do. So I need to take the 36th root of 1.276. And really, I can think of that as 1.276 raised to the power of 1 over 36. Sometimes it's easier to do that in a calculator than it is to type in a 36th root. And these two things are equivalent. So once I find what that number is, that'll equal 1 plus R over 12. So let's figure out that decimal. So 1.276, or the 36th root of 1.276, is 1.00679. It's approximately equal to that. There's a few more decimals after that, but we're going to just round here. And then I just need to subtract 1 from both sides. And so I have 0.00679 equals R over 12. And then I just need to multiply both sides by 12 to solve for R, which remember, R is that annual interest rate. So I get, when I do that, I get R is equal to 0.0815. well, maybe I'll go one more decimal, 0.08152. Okay, so that is the rate as a decimal, but if you want to think of that as a percent, we'd have to multiply this by 100, which is move the decimal 2 spaces. So the rate was about 8.152%. That was the annual interest rate that allowed her investment of $1,000 to grow this much to $1,276 within a short period of time, 3 years. So that must have been the annual interest rate. Okay, so now that I have the annual interest rate, I can now turn this into an equation, a model. Okay, so we're going to use that rate to now form a model. Now remember, in a model, the final amount is the variable. It's like the y value. And the time is like the x value. So those are the only two variables when you're thinking of this as a model. So we can think of that as the final amount as a function of time, right? The y value, a, of t, meaning a function of time, is equal to that initial amount Julia invested, 1,000, times 1 plus this interest rate that we just found. So I'm going to turn it back into the decimal, because when you plug it into the formula, it should be in decimal form, divided by 12, raised to the power of 12t. So when we're using a model, only the a and the t remain as variables. Those are really our only true variables in these formulas when we have some of the other information. So this is now fixed, right? The amount she invested is not going to change. She invested $1,000. That's what she did. The interest rate, now that we found it, is not going to change. It's the same interest rate. And the fact that it's being compounded monthly is not going to change. But we can see what that amount could be given different times. So the time that the money sits in there could vary. And then the final amount will depend on that. However long the money sits in the account produces a different final amount. And so what we're trying to do is figure out, well, how much will that be after a different amount of time, after 5 years? So what I'm going to do is take this model and plug in 5 for t. So we're going to find the final amount as at 5 years. So amount evaluated at 5 years, a as a function of 5. And so that's 1,000. And let's go ahead and figure out what this would be as a decimal. So it's 1.00679 to the power of 12 times 5. And then we just need to plug all of that in our calculator. So the amount after 5 years is equal to, maybe I'll simplify one last thing, 1,000 times 1.00679 to the power of 60. And then I'll plug all of that into the calculator. And so that is going to equal, so it's about $1,500.84. So after 3 years, the amount had gone to this number, 1,276. If we assume it's the same rate being used and that it's still compounding monthly, then after 5 years, she would have a total of $1,500.84 in her account. Okay, so now I'd like you guys to try one. The last one, I'd like you to try it on depreciation. So you'll use the same formula for appreciation, except when you plug in the 15% for R, remember to plug it in as 1 minus that number. 1 minus R instead of 1 plus R. But go ahead and try this one. Okay, so you can check your answer here, see if you got it right. For the first part, how much will the car be worth after 6 years? I got that it would be about $10,843 in value, approximately. You can see here, the main thing I want to draw your attention to is right here. So it's the same formula for appreciation, but instead of adding 15% to 100%, I'm subtracting 15% from 100%, leaving me with 85%. So what this is really saying is that at the end of each year, the car is only worth 85% of what it was at the beginning of the year. And so that's how it kind of goes down each year, decreases each year by 15%. Then for part B, when, we were looking for time, when will the car be less than 5,000? Well, to find out when it's less than 5,000, I just go ahead and plug in actual 5,000, and then I just make my answer longer, more time than what I get when I solve for when it's equal to 5,000. So anyway, I just plugged in 5,000. I had to divide both sides by 28,750, and I got this decimal here, 0.1739, which was equal to 0.85 to the power of t. trying to solve for the exponent. So that's when we bring in logs. We rewrite this in log form. So as a log base 0.85 of this result, 0.1739, plug that in my calculator and got about 10.76. But that's how long it would take to get down to exactly 5,000. So when would it be less than 5,000? Well, let's just go round it to the next whole year. It would take about 11 years. By the time 11 years have passed, the car's value will now be less than 5,000.